Hello everyone, myself Dr. P. Vijayakumar, Associate Professor, Department of ECE, Aditya University. So in today's session, we will be seeing the types of random process based on the parameter stationarity. So the types are first order stationary random process, second order stationary random process, Whiteson stationary random process, jointly Whiteson stationary random process, and Schrittson stationary random process. And also we will be solving few example problems to identify the type of the stationarity based on the statistical parameters and based on the mathematical definitions. So at the end of this lecture, students will be able to learn the classification of random process based on the parameter stationarity. That is nothing but classifying the types of stationary random process. And another learning outcome the students will be able to learn is classifying the types of ergodic random process. We will define what is meant by ergodic random process, and also we will classify the ergodic random process, and also we will try to relation between stationary random process and ergodic random process. Okay. So in the earlier session, we have seen the mathematical definitions of stationary random process, first order stationary random process. When do we say a random process is first order stationary? When a mean of the random process is constant. When you compute mathematically the mean of a random process, if it is constant, then we can conclude it is first order stationary random process. And also we have seen the definition of second order stationary random process. So a random process is said to be second order stationary if we compute the autocorrelation function, if autocorrelation function is a function of tau, if it is a function of time difference. It should not be a function of absolute time, it should be a function of time difference. Tau is nothing but time difference. So if it is that, we call it as second order stationary random process. If both conditions, first order stationary, second order stationary, both are satisfied, we call it as Whiteson stationary random process. It is quite used frequently. And one more thing is jointly Whiteson stationary random process. If two random processes are different, if you take two random processes x of t and y of t, if the mean of the random process x of t is constant and the mean of the another random process y of t is constant, and if you compute the cross correlation function, if cross correlation function is a function of time difference tau, tau is nothing but time difference t2 minus t1, then we call it as if all 1, 2, 3. If all these three conditions are satisfied, we call it as jointly Whiteson stationary random process. Generally, this is measured between two different random processes. Here we have taken two different as x of t and y of t. Next, Schrittson stationary random process. So already we have seen the definition of density function or representation of density function. If nth order density function of a random process is not changing with the time, then we call it as Schrittson stationary random process. So up to which order it satisfies, we will call it as Schrittson's up to that order. For example, if kth order density function random process doesn't change with the time, we call it a Schrittson stationary random process up to the order k. So depends. If completely for n variables it is satisfied, generally we call it as Schrittson stationary random process. Let us see how to identify the random process stationarity based on some mathematical examples such that we can easily understand. For example, we are taking a problem is given like this. Identify whether random process x of t is Whiteson stationary or not. So we need to recall the mathematical definition of Whiteson stationary. What is that one? First condition is the mean of the random process x of t should be constant, and the second condition is autocorrelation function of the random process must be a function of time difference. Then we say that the random process is said to be Whiteson stationary random process. So the condition 1 and condition 2 satisfies, then we call it as Whiteson stationary random process. Let us check the condition 1. So the condition 1 is I want to compute the mean value. So what is the formula for mean? And given phi is a uniform random variable over the range 0 to 2 pi. We know the uniform density function fi of phi is equal to 1 by 2 pi minus 0 over the range 0 less than 5 less than 2 pi. So as per the definition of uniform density function, the density function is fi of phi is equal to 1 by 2 pi. So expectation. So what is the formula for expectation of x is equal to minus infinity to infinity x into fx of x is to t dx. Applying this one, you can see here fx of xt is 1 by 2 pi, which is a constant. I am bringing outside the limits, and the limits are from 0 to 2 pi, and the function x of t is sin omega t plus phi. Is it correct? Okay. So, the integration of sin is cos omega t plus phi, and if you substitute the limit 0 to 2 pi, we know that the cos 2 pi is 1 and cos 0 is 1, 1 minus 1 0. So, the expectation of the given random process x of t is equal to sin omega t plus phi is 0, which means the random process expectation E of x of t is constant. So, the condition 1 is satisfied. Next, let us check the second condition. So, what is the second condition? We need to compute the autocorrelation function. Autocorrelation function is mathematically defined as Rxx of t comma t plus tau, expectation of x of t into x of t plus tau. So, sin omega t plus phi, sin omega t plus tau plus phi. So, we know the formula of sin A, sin B can be written as 1 by 2 cos A minus B minus cos A plus B. And already we computed expectation. We know that expectation of constant is a constant. So, expectation of cos omega tau is 1 by 2 cos omega tau. Next, we need to compute the expectation for this one. Expectation of cos 2 omega t plus omega tau plus 2 phi. So, the integration of cos is sin 2 pi is 0, sin 0 is 0. Overall, you will get 0. So, this term will vanish. The remaining term is 1 by 2 cos omega tau. Clearly, it is a function of time difference and it is not a function of time. So, the second condition is also satisfied. So, both condition 1 and condition 2 are satisfied. Then we can clearly say the given random process x of t is a wide sense stationary random process. So, these are the two mathematical things we need to verify to conclude the given function is a wide sense stationary random process or not. And let us see one more example related to computation of mean and autocorrelation of a given random process. The random process given as x of t is equal to a. Given it is a uniform density function which is ranging over 0 to 1, 0 less than a less than 1. So, clearly the uniform density function is 1 by 1 minus 1. So, it is nothing but 1. Okay. Now, fa of a is simply 1. Now, the limits are from 0 to 1, 0 to 1, 0 to 1, a into 1. Integration of a. Now, this is a function of a and integration also we are doing with respect to a square by 2. Substitute the limits of values, you will get 1 by 2. So, the mean value what we got? A constant. Mean value we got a constant. I can say this as first order stationary random process simply. Next one, autocorrelation function, expectation of x of t into x of t plus tau. X of t is a, x of t plus tau is a, expectation of a square. So, we know the formula fa of a is nothing but 1 over the range 0 to 1, a square into 1, integration of a square a cube by 3, 1 by 3. So, e of a square or nothing but correlation function, what we got? Correlation function is a function of is constant simply, it is a constant and mu x is also constant, both are constants and clearly they are satisfying the wide sense stationarity conditions. So, we can conclude it is a wide sense stationary random process. In a similar manner, we can compute or we can verify the stationarity simply by computing the mean value and correlation value. Next, we will see the problems related to jointly wide sense stationary random process. Jointly, it is not jointly completely, but here x of t is a function of two functions. X of t is equal to a sin t, b cos t. Here it is given that a and b are independent random variables with 0 mean and equal distribution. 0 means E of x is 0. Okay. Equal standard deviation means the standard deviation is some constant, let us say some sigma square. Okay. So, here two variables are there, two random variables A and B. Now, expectation of A is 0, expectation of B is also 0, both are zeros, and sigma A square is equal to sigma B square, and which is equal to some constant sigma square. So, this data is given to us. Now, let us verify and let us see whether it is stationary with order 2 or not. First, we are computing the mean value of the given random process. Expectation of A sin t plus B cos t. I can write this as expectation of A into sin t, expectation of B into cos t, and expectation of A is given as 0, expectation of B is given as 0. Overall value will be 0. Next, to verify the second order stationarity, we need to compute the autocorrelation function. The formula for autocorrelation function is E of x of t into x of t plus tau. Applying the formula and multiplying the terms, what we will get? E of a square, E of ab, E of ab, E of b square, given that independent random variables. So, when the random variables are independent random variables, E of x5 is 0. That means E of AB is 0. That is also given in the problem itself. Next, variance formula, E of A square is equal to E of B square is equal to sigma A square, sigma B square is equal to sigma square. Substituting the value sigma square into cos t plus tau, sigma square sin t into sin t plus tau. Now, this is of the form cos A cos B plus sin A sin B. I can write this as cos A minus B, cos of t plus tau minus t. So, sigma square cos tau. So, the second order parameter what we have computed, autocorrelation function. Autocorrelation function is clearly a function of time difference and the mean value is equal to some constant. So, clearly both conditions are satisfied, then we call it as second order stationary random process. So, simply by computing the mean value and autocorrelation function, we can conclude whether the random process is first order or second order. Here both conditions are satisfied, that is why we are telling it is a second order stationary random process. Before going to the ergodic random process definition, we need to see some basics. So, we need to see what is meant by a time average and what is meant by an ensemble average. So, you can see here so many sample functions are there. The average of all the sample functions we call it as ensemble average. Whereas here you can see the random process, at different time instants we are taking the random. So, if we are averaging over a time, we call it as time sample function. Here it is a statistical average, whereas here it is a time average. Based on the time we call it as time average, simply based on the statistics we call it as statistical average. Okay. Ensemble average is equal to statistical average, which is different from time average. And also let us see the mathematical definitions of time averaging functions. The time average function, you can see here averaging is based on the time parameter. Autocorrelation function also, averaging is based on time parameter. Cross correlation function. In general, if it is a ensemble autocorrelation function, how do we write? Rxx of t comma t plus tau is equal to expectation of x of t into expectation of t plus tau. Okay, simply we do like that, but here we are computing the time averages. Okay, time average is different, ensemble average is different. So, you can clearly see the difference here. This is ensemble average, this is time average. This is ensemble autocorrelation function, this is time average autocorrelation function. This is ensemble average cross correlation function, this is time average cross correlation function. The mathematical definitions here, the averaging is done with respect to time. Okay. Here the average is based on the statistics simply. So, we will see the definition of ergodic theorem. The ergodic theorem states that for any random process x of t, if all the time averages of a sample function is equal to corresponding statistical averages, then we say the random process is ergodic random process. So, time average must be mathematically equal to ensemble average, all the statistical parameters. If time average functions is equal to statistical average functions, then we call it as ergodic random process. and it is nothing but ergodic theorem. Any random process which satisfies the ergodic theorem, we name it as ergodic random process. Okay. So, ergodic random process is also classified into 3 types. So, there we have seen different types of stationarity random process. Here ergodic random process is classified into 3 types. Based on the mean parameter, it is called mean ergodic random process. If ensemble average is equal to time average, then we call simply it as mean ergodic random process. If autocorrelation function, ensemble autocorrelation function is equal to time average autocorrelation function, then we call it as autocorrelation ergodic random process. And similarly, ensemble cross correlation function and time average cross correlation function, both you take. If both are equal, then we call it as cross correlation ergodic random process. So, ergodic random process are classified into 3 types: mean ergodic random process, autocorrelation ergodic random process, cross correlation ergodic random process. So, this is an example of an ergodic random process. A sonar ecosystem on a submarine transmit a random noise to determine the distance and the target. So, here we are finding the time average, which is related to ergodic random process. The round trip time we are calculating and we are computing the time average, and based on those time averages we compute the or determine the distance of the target submarine. So, this is an example of a ergodic random process. In this session, we have seen the definition of stationary random process and types of stationary random process, first order, second order, White's and stationary, and next we have seen few problems related to stationary random process, how to identify the first order stationarity, second order stationarity, simply how to compute the mean and autocorrelation for a given random process. We have seen few examples. So, after computing mean and autocorrelation function, we can conclude if mean is constant, first order stationary; if autocorrelation function is a function of time difference, second order stationary; if both conditions are satisfied, we call it as White's and stationary random process. Okay. Next one is ergodic random process. We have seen the formulas: time average autocorrelation function, time average cross correlation function. If all time averages is equal to the statistical averages or ensemble averages, then we call it as ergodic random process. If both means are satisfied, mean ergodic random process. Time average autocorrelation function satisfied, we call time autocorrelation function ergodic random process. If cross correlation function is satisfied, cross correlation function ergodic random process. Like this, we can classify the ergodic random process. So, in the next session, we will be seeing the temporal characteristics of random process. The temporal characteristics already we have seen. The statistical parameters are mean, autocorrelation function, cross correlation function. We will see in detail about what is meant by autocorrelation function, what is meant by cross correlation function, and we will see some properties and problems related to correlation functions in the next session. Thank you.